Indeed. So I'm going to spend the next sort of 20 minutes talking about mostly about self-gravitating disks, which Kathy has really nicely introduced for us. So I'm going to start off by giving you a little bit of observational context. I'll then talk about three different areas: triggered fragmentation, migration of planets in these disks, and then also how planets in disks can affect the disk structures. So to start off with, here we have a few lovely observations, which I think kind of help to motivate the idea that we need to consider self-gravitating disks. So on the left-hand side, in the middle plot, you see images of gaps and rings. These are relatively young disks, especially the middle image. And if these rings are formed by planets, then of course we have to think about planet formation when the disks are very young. The image on the right-hand side by Farzana et al. Presents, what they do is to actually suggest that the inner part of the disk, the CO in the inner part, is actually shielded by millimeter grains. And if we have millimeter grains in such a young disk, then at least we have to think about the idea of dust growth when the disks are quite young. We've seen these two images already, so I won't I'll be talking more about the Elias disk here. Again, Kathy's already talked about this, this disk with a fragment that's formed just here. This is a stellar mass object that's formed by disk fragmentation, again motivating the idea that we need to think about young disks. So, Elias 227. This was a very interesting observation that came out a couple of years ago now. And what this disk has is some very, very large scale spiral arms. I'm just looking for the pointer. Not sure where it is. Okay, right. So we have large-scale spiral arms. I'll just try with my arms, even though I'm short. And you see these arms go out to about 300 AU. And so what we tried to do in our group was to try to understand. Sorry, thank you. Was to try to understand what was actually causing these spiral arms. So generally, trying to describe, trying to figure out what could form, this morphology. And we came up with sort of two ideas. One is that it could be a self-gravitating disk. These images were sort of, what we were trying to do was just generally try to match some of the features, but not go into detail of the exact kind of disk properties. But you can see that we're able to sort of reproduce these spiral arms with a gravitationally unstable disk. Although that's not the only solution, we were able to see that you could, in fact, form these spiral arms with an external companion, a large planetary mass companion. So, well, how do we actually distinguish between these two possibilities? Well, there's some earlier work that's been done that can actually help us with this. So we can look at the spiral morphology. Now, what was shown back in 2002, and this is a nice sort of pictorial view of this, is that if you look at the pitch angle against radius, and here is where the companion's located at r equals 1, you can see that interior to the companion, the pitch angle changes with radius. In fact, exterior as well. For the Elias case, we're concerned with an external companion, so we're thinking about how the pitch angle might change in the inner part of the disk. But on the other hand, we also know from self-gravitating disk simulations by Peter Cousins that if you have the spiral arms in these disks are in fact well described by a logarithmic spiral with a constant pitch angle. So what we in fact did in this paper with Duncan Falcon was to actually look at those simulations that I presented on the previous slide, and actually try to try to understand whether those were in fact logarithmic spirals with a constant or a varying pitch angle, and they were indeed. If we just go back to this image here, these self-gravitating disk simulations were in fact consistent with a a constant pitch angle, whereas we weren't able to describe the companion case with a constant pitch angle very well. The Elias 227 observations that we know of so far, certainly also the high resolution ones that have come out, do in fact show that these disks do have a constant pitch angle. So it's certainly consistent with the idea that it could be a self-gravitating disk. Now, kind of continuing on with the motivations for studying young disks. Well, Kathy's already shown this image here. We have a hot Jupiter here in the inner parts of this disk. This is a relatively young disk. The disk on the right-hand side isn't that young. It's about 5 million years old, but I just put it up here just to show you that we have two images or two detections of planets in disks. So really, we're just at the beginning of this, and hopefully sort of that's going to continue further into the future. But what we do have is indirect ways of trying to deduce whether we have planets in disks. So we have some fabulous images that you've seen already in the previous talks. Overwhelmingly, we're seeing gaps and rings in these disks. And of course, one of the obvious possibilities is that these gaps may harbor planets. So there was a really nice study by Giuseppe earlier this year, where he actually put together the planet masses that you can infer if you were to assume that there was a planet in each one of these gaps. And what he's done is to overlay the results, these are the colored points here, against the exoplanet population that we've detected. These are the black ones here. So we've got planet mass against radius. And what's sort of the most striking feature of this plot is that these newborn planets, these early planets, really seem to have different properties to at least the planets that we have detected. So I'm going to sort of continue presenting this talk in the way of sort of challenges that I think we need to address when it comes to self-gravitating disks. And the first challenge here is this sort of population of planets here. They're sort of at tens of AU. They're quite far out. They're quite massive, sort of super Earths and Neptunes and upwards. And the question is, how do we actually form these planets at large distances? And in some cases, some of those disks are quite young. So also in young disks. And Kathy already talked about this in detail, so I'm just really going to put up sort of my my thoughts on this. Is that I do think that we need to consider dust growth in young disks. So I'll move on to the next topic that I want to discuss, and this is the idea of triggered fragmentation. So I'm going to come back to this plot that that I showed a minute ago, and ask a different question. So I'm going to highlight now these objects that are higher up, more massive objects at what I refer to as sort of intermediate distances, sort of kind of 30 AU-ish. And the question is, how do we actually form these giant planets at intermediate distances? Okay, so they're massive, they're reasonably far out that it might be somewhat difficult to form these by pebble accretion. They're not so far out that we can form them by gravitational instability. So what I'm going to suggest is that perhaps these could have, the idea of triggered fragmentation could contribute to this. So what actually is triggered fragmentation? Here is a movie of one of these simulations. What we have is a fragment that forms in the outer parts of these disks. This is the black dot that you see moving around. As a result of this planet, this fragment being embedded in this disk, it actually causes the disk to become very, very dynamic. It causes material to move outwards, it causes material to move inwards. And that inwards movement of material essentially drives a lot of mass onto an inner spiral. That inner part of the disk was sort of marginally stable, but it kind of pushes it into a state of instability and causes a fragment to form. So we can actually look at this same movie, but in the radial velocity rendered plot. So this is showing you, so if the blue and black parts are material that's moving inwards, the sort of orange and yellow parts are material moving outwards. So at the very start, you see that the disk is quite calm. Eventually you get a fragment forming. Once the fragment forms, you actually see more regions of black and white, the more extremes of this color scale, and you actually see that it's become much more dynamic, and sort of this is where you see sort of material having moved inwards to then then form that fragment. So, sort of linked to the idea of how do you actually form these objects at sort of intermediate distances. Another aspect is that we really don't know the details of triggered fragmentation. There was some earlier work done by Phil back in, I think it was 1999, and then there was sort of my study done in 2015. But we really need to sort of think about the details of this in much more, much more thoroughly. Sort of thinking about where do they actually form, what are the mass of these objects, and can they actually, is it only an internal trigger that causes it? Something that Kathy and I have been discussing is whether or not an external trigger can actually cause this. And really, how common is this process? We have no idea at all. So the next topic that I'd like to discuss is the idea of, once we've formed an object in self-gravitating disks, what happens next? So thinking about the migration and the survivability of these planets. So this is a simulation by my PhD student who's sort of investigating this. This is just a simple self-gravitating disk modeled with beta cooling, and what he's essentially doing here is sort of reproduce past results where he finds that planets just migrate in incredibly rapidly. This is actually work that we've done quite a few years ago, where you can actually see here we have the separation against time, and these are many simulations sort of plotted on one graph. For a Jupiter mass planet, you see that these planets just migrate in just within a few orbits from when we let them go. So we in fact I had another student that actually looked at this in a little bit more detail, and what he actually found was that it was really, really hard to open up gaps in self-gravitating disks. Even 45 Jupiter mass objects didn't open up gaps. So this is really, really difficult. And the reason why he was finding this was as follows. So here's my schematic diagram of the planet in a disk. This is a surface density. And what you have is that as the planet when the planet is embedded in the disk, it's trying to carve out a gap. So this is my sort of little gap that it's carving out. But at the same time, it's also migrating, so it's moving inwards in the disk. Now, if it moves in too rapidly, then it's simply going to move out of that region where it started carving out the gap, and it will have to sort of start the whole gap opening process again. But if the timescale on which the gap can open is much less than the timescale on which the planet migrates, then it will in fact open up a gap and survive. So there's really a timescale issue here that we also need to consider. And this is especially relevant for self-gravitating disks because they're very turbulent, they're very massive, it's so much harder to open up gaps. So I've sort of expressed a bit of a bleak picture of planet survivability in these young disks. So even if we could get them to form, we need to think more about their survival. But what we're actually looking at in more detail with my students' PhD thesis is to actually model these disks in a more realistic way. Those ones that were modeled before were entirely turbulent from the outside all the way to the inner parts of the disk. But we only expect the outer parts of these disks to be self-gravitating. The inner parts should, in principle, be much more much more quiescent. In addition, we have other aspects that various people have considered, the cooling, whether or not multiple fragments can actually help planets to survive. That's another area that my student will be looking at. And of course, planet growth. Dimitri actually showed in 2015 that there's some chance that actually it's more likely to survive if the planets are larger. Sorry. That's fine. That's fine. Okay, so that brings me to my fourth challenge, which is how do planets actually survive in these young disks? If we expect them to form, we have to think about whether or not they survive. So the final aspect that I'd like to touch on is some work that we'd done on how planet migration affects disk structures. Now, this work was not actually done for self-gravitating disks, but I'm going to talk about it, and then the important point that I want to make is that we also need to think about this in the context of self-gravitating disks. So, from planet disk interaction simulations, we know that if you have a planet embedded in the disk, it should open up a ring exterior to it. This is work that has gone, that has really started early on back in 2004, and a lot of authors have shown this. Now, this is a study by Giovanni Rossotti, where he actually shows this, but other authors also show this. So the planet is at R equals 1. This is the surface density. And what he shows is that you get a ring exterior to the planet at whatever, in many of the different particle sizes that he considers. But the question we started asking was, well, what happens to the dust ring when the planet migrates? All of the simulations that have been done prior to this, or many of them, had actually not considered the motion of the planet, and that was the right thing to do because we needed to understand the whole process of dust collection in the vicinity of the planet. So we modeled. We took Giovanni's simulations, we modeled them with a migrating planet, this time with rather than a stationary planet. And here are some of the differences that we found. So starting off with the gas surface density against radius, 0.75 is where the planet is. The red line shows you what you have if you have a planet that's stationary, and by that I mean it's orbiting at a fixed radial location. The blue line is the migrating planet simulation. Now, the first thing to notice is that the pressure trap is weaker in the outer part of the disk. And the second aspect that's different, and this is a very subtle difference in the gas profile, is that you actually get this sort of little plateau in the blue line when you have a migrating planet. So just a minor difference in the pressure profile. But the difference can be quite significant. So in the outer part, that reduced pressure maximum results in a reduced dust concentration, and the inner part can lead to a dust enhancement, as you see in the blue line. I think this has moved again. Sorry. Okay. Okay, so this is just for one particular particle size. Sorry, I think it's not staying off. Is that simpler? Sorry. Yeah, that might be. You can just leave it in there if that. There you go. Is that on? Right. Okay. Perhaps that's better. Okay. So I let me see if I can handle three things at the same time. Okay, so I showed here that you have a dust enhancement in the inner part, a reduced concentration. This is the blue line I'm referring to in the outer part. But this is just for one particular particle size. what we can do is now look at what happens for different particle sizes. For the small dust, what we found was something quite surprising. We didn't find the exterior dust ring, as you've seen in the previous simulations, as we've seen for many years. But what we did see was an inner dust ring that you see here. But for large dust, the results were as we've seen before. So the planet is located here, and you have an outer dust ring. So that's no different to what we'd seen before, but the left-hand side was really quite different, and that was specifically for small dust sizes. Well, why does this actually happen? Well, the answer is really to do with the relative difference between the planet's velocity and the dust drift velocity. Okay, so so here what I'm doing is plotting the velocity of the planet here. That's the dotted line. The planet is located at r equals 0.75. And what you see in the outer parts of the disk, the dust velocity is much smaller than the planet's velocity. Okay, so this is moving inwards here. It's moving much more slowly. So what we have, when you've got a planet in the disk, it has its pressure maximum. So imagine the star is over there. The pressure maximum is exterior to it, and it's moving along. It's dragging its pressure maximum along with it at the same rate. If the dust in the outer part of the disk can drift rapidly enough, it can keep up with that moving pressure maximum. But if it can't, then it's simply not going. If it's drifting too slowly, it's just simply not going to keep up with that pressure maximum, and it won't form a ring in the outer part. And that's exactly what's happening with the small dust. It's drifting in too slowly. It's simply unable to keep up with the pressure maximum. On the other hand, in the inner part of the disk, things are a little bit different with the small dust. You see that it's the planet's in fact sort of sweeping up the dust, it's sort of pushing it into that little pressure lip that we saw in the inner part of the disk, and as a result, you can actually collect small-sized dust there. On the other hand, the large-sized dust is a little bit different. So now you see that the dust velocity is faster than the planet velocity. It's able to keep up. This is in the outer part of the disk. It's able to keep up with that pressure maximum and actually form that ring. On the other hand, in the inner part of the disk, this dust is just traveling way too fast. So it moves in, it collects in that pressure. It's actually a pressure sort of an enhancement. I'm just going to go back a few slides just to go back to the pressure. So this is gas surface density, but it's equivalent to the pressure. What you see here is that it's always a negative pressure gradient, so the dust is always moving inwards. It doesn't actually ever get trapped, but it just slows down at this sort of point of inflection here. Now, all the dust slows down, but because the large dust is moving faster, it continues moving into the inner part of the disk. It continues moving into the inner part of the disk and just ends up draining onto the central star. So we took these simulations one step further to try and understand whether or not we could actually observe whether we could observe a migrating planet. And this is some excellent work done by an undergraduate student in Cambridge, where she shows that there are 3 outcomes. So the first sort of 3 observational possibilities. The first is what we see on the left-hand side. So we have a gap a gap with a ring exterior to it. This is these are ALMA mock observations. Now that's nothing different to what we've expected before. This is where we would say that we would have a slowly migrating planet or perhaps a stationary planet. The second possibility is that you have a ring interior to the planet. Sorry, interior to the gap. We wouldn't know if there's a planet there. If you've got a ring interior to a gap, so far we do not know of any other way in which you can actually form a ring interior to a gap. So that we are suggesting is an unambiguous detection of a migrating planet. However, the parameter space in which we would expect that to happen is in fact somewhat limited. And so the more likely observational outcome that we might see as a result of a migrating planet is a double ring structure. Okay, so this is the middle panel that we have here. But then you could ask the question, well, what's the difference? How do you know that it's, if you see a double ring, how do you know that it's a migrating planet versus a low mass planet in a disk which can form multiple gaps and multiple rings, or a or two planets in a disk? Well, the answer comes when you actually look at the spectral index. If you've got, in this particular case, you actually end up with the smaller mass, the smaller grains in the inner part of the disk and the larger grains in the outer part of the disk. And if you look at the spectral index, you would actually end up with a higher spectral index in the inner ring compared to the outer part. The dotted line is again where the planet is. But for the other two scenarios that people have presented for multiple gaps and rings, you would in fact have the opposite, because you would expect large grains in the inner part and smaller grains in the outer part. So this brings me to my final challenge, where I think we need to address. Well, this is the first part, is really a challenge for observers. Can we actually see evidence of migrating planets in disks? But the second part is, can we actually, as theorists, can we figure out if we can even constrain the speed of those migrating planets? So with that, I'd like to bring you to my summary slide. I started off by giving the observational motivation for studying young disks and the importance of studying those. The first challenge I presented was to ask about how we can actually form super Earths in young disks, and also at large, specifically at large distances. And the proposal that I said was that I think we need to think about the dust growth side of things when it comes to that. The second challenge I asked was, how do we form giant planets at somewhat intermediate distances? And I proposed the idea of triggered fragmentation, and we in fact need to understand the details of triggered fragmentation in more detail. And then the fourth challenge I put out was, how do planets in fact survive in these disks? We need to think about the migration of planets in young disks. And then finally, I talked about trying to observe migrating planets, and can we in fact constrain the speed at which they're migrating? So with that, I'll thank you for your attention, and I'll take any questions. Yeah, sure. So apologies. So let's go back. The small dust in we modeled, so large dust, we modeled Stokes numbers up to 0.1, and small dust we went down to 10 to the minus 4. Sorry, here. Sorry, 10 to the minus, we did go down to 10 to the minus 4, but those actually just followed the gas. These ones were, I think, 10 to the minus 3 or 10 to the minus 2. So just to sort of put this in context when it comes to actual sort of real observed disks, the transition between small dust and large dust, sort of the inner ring to the outer ring, would typically happen at about millimeter sizes for a typical sort of a 30 Earth mass planet at about 30 AU in a typical protoplanetary disk.
I'm not sure if I understood all the scales, but in the case where you do form an inner dust ring, so you're migrating, I guess, slowly enough to capture on the way in, would the surface density in that ring give you some information on how far you've migrated and how much you've sort of swept up on your way in?
I'm not sure, because I think that would highly depend on initial conditions. We haven't yeah, I wouldn't want to go further with that one. I think we haven't done that. We haven't done that analysis, so I wouldn't be sure about that one. But I suspect that will depend on initial conditions a lot.
If I understand, so the reason why you have the inner dust ring is because the dust is moving, the small dust is moving slower than the planet. But if this dust is small, then it should move with the gas, with the gas radial velocity. So this essentially implies that the planet is moving faster than the gas. So this would be so the planet migration would be faster than the viscous rate in this case. Is this the case?
So I'm not sure if I totally understood, but let me just firstly, for the very, very small dust, indeed it does move with the gas. So these are slightly larger dust sizes, which still can be affected by which still can be affected sort of by the pressure perturbations independently of the gas, and are not sort of totally tracing the gas motions. So these ones, the dust, it's sort of, the way to sort of see it is that they are, yes, here they're moving a little bit slower, here they're actually moving faster. It's basically, the idea is that it's sort of being snowplowed by the planet. It's being snowplowed and sort of pushed into that sort of pressure perturbation where they are then slowing down.
Well, I guess my question in the end was whether the planet is moving with the viscous rate or not.
We move the planet at a type 1 migration rate.
Type 1?
Yes.
Okay,
yeah.
okay, okay.